the introduction. Everything's working. Okay. Yeah, I'm going to talk about energy dynamic graph algorithms. So I prepared one slide, talk about dynamic graph algorithms, introduce them. But I think those are familiar to, well, there's everyone here in the room. So I just want to make sure that we're all on the same page here. I assume that we have a dynamic graph algorithm, which is actually a data structure. So it gets to see the graph first at some point, which we call the initialization phase, and then it can produce an output, so compute something on it, and then later on it only gets to see updates of the graph, and then we assume that it produces only it tells us only how the output changes in response to those updates. We also assume that the output is generated in response to a query. So the query might be explicit, like tell me something about the graph in its current state, or implicit. So whenever I do an update, I expect my data structure to just output in the solution or the difference to the previous solution. So what I mean by an update is insertion, deletion of a single edge, or the change of its weight by some delta unequal to 0. So either weight increases or decreases. A batch is just a group of multiple updates in some order. The updates can be mixed as well. And I will assume that a batch always contains at most one update to every edge. So it cannot happen that within a batch, an edge is modified twice or something like that. And the updates and batches arrive one at a time, and they are unknown to the algorithm beforehand. So the algorithm does not know what's coming. And then I'm going to talk a bit about recourse. We've had that term previously, so this is just to remind you, by recourse I mean the number or the size of the changes introduced to the solution due to an update or a batch of updates. So in fact, the size of difference between the previous solution and the next solution. Right. So in this talk, I would like to talk about two examples of large areas I'm interested in. So the first area is dynamic algorithms for data centers. And here I picked a problem that deals with disjoint matchings and KH coloring. The second area I'm interested in, a second area I'm interested in are dynamic algorithms for basic problems. So here I picked a very basic problem, reachability. And then at the end, I want to come back to the title of this talk, actually. So I want to say a bit about what it means to engineer dynamic graph algorithms. All right, so let's start with the first topic. So within a data center, we have usually a lot of applications running, modern applications such as distributed machine learning or data mining, or also if you want to access remote resources like GPU or memory that's not local to the machine, that our applications are currently running on, then this requires large data transfers. And actually, it has been shown that these communication between different machines within a data center is actually a bottleneck to efficient computations within such a data center. So usually, we have a situation that within a data center, we have a set of top-of-rack switches that are typically connected by a fixed topology. So it's not really important for this talk what this topology is. It could be some tree-like structure, for example. But yeah, as I said, it's not really important. You can assume that they are all connected to each other. They can all communicate with each other, but not necessarily equally fast. So what one could do, or what one can do, is introduce or use additional technology, like, for example, optical switches. An optical switch is able to establish additional direct connections between such top-of-rack switches. They have very high bandwidth, and they are reconfigurable within microseconds. So they can connect pairs of such top-of-rack switches at one point of time, and then you reconfigure them, and then they compare a different set of pairs. And of course, we can have just one optical switch, but multiple. So the key question here is, how do we configure those optical switches optimally to offload a maximum amount of communication demand to those optical switches? So, well, in order to attack this problem, we can look at the communication demand graph. So on the right here, we have a graph having a vertex for each top-of-rack switch. And then we have an edge between two vertices with a certain weight, and the weight corresponds to the communication demand. So when we have an optical switch that connects pairs of vertices, or vertex corresponds to a top-of-rack switch. So if we have such an optical switch, then in fact this corresponds to a matching in our communication demand graph. And if you want to offload a maximum amount of communication demand to those optical switches, then we are looking for a heavy matching, a matching of large weight. And when we have a second optical switch, well, then we just have a second matching in the graph. So in fact, we can say that each optical switch corresponds to a matching in the graph, or we could also say we are trying to color the edges of our communication demand graph using as many colors as we have optical switches. So we can model this problem either as finding a set of k disjoint matchings of maximum total weight, or we could say we're looking for an edge coloring using k colors. So we try to assign to each edge either one of k colors or bottom, meaning that this edge remains uncolored, such that well, each coloring is a matching, and in total, all colored edges together have a maximum weight. We also assume in this setting here that we have like a centralized controller that is able to observe the communication demand between our top-of-rack switches and can reconfigure the optical switches. So we end up with, well, the weighted k-edge coloring problem, or we could also call it a weighted k-disjoint matchings problem. Given a graph with edge weights W, find a k-edge coloring that maximizes the total weight of the colored edges. Okay, well, of course, this is not a static problem because the communication demand and therefore the edge weights change over time. It depends on the application that we're running, that is running on those servers in the data center that determines, well, who communicates with whom. So there may be changes. For example, we might have this solution here, this configuration, and then for one pair of nodes, the weight decreases, so we have less communication, but it increases for another pair of nodes. So there are two things that we can do. We could either just recompute from scratch and just take the modified graph, compute a new coloring after a certain number of weight changes, or we could try to update our current coloring. Of course, if we update our current coloring, we hope that we only need to consider the part of the graph where the changes actually occur. So this should lead to a speed up in computation. And second, we can avoid unnecessary configuration changes. So each configuration change means that I have to reconfigure these optical switches. Maybe previously the connection was established by the first optical switch, and now I just move it to the second optical switch. This may be completely unnecessary. So I'm also trying to have as few recolorings as possible, which should lead to a speed up in configuration. So what is known about this problem? First, okay, there's a sort of obvious connection to the weighted matching, which is a special case where we just have one color, or we're looking for one matching, and we all know that this is efficiently solvable and also very well studied also in a dynamic setting. On the other side, we have the edge coloring problem, which is one of the classic NP-hard problems. And here one could say, okay, if I set k, the number of colors, to the maximum degree and all edge weights to 1, then I get exactly the classic problem. So we're somewhere in between these two problems. But it turns out that the radial edge coloring problem is NP-hard and also APX-hard already for k greater equal 2. So when we want to solve this problem in practice, it makes sense to look at approximation algorithms or heuristics. And also, this problem has been studied also experimentally before. In fact, we did this 2 years ago and looked at this problem just from a static setting where we don't have any changes in the edge weights. Okay, so here we tried to come up with intelligent and fast, fully dynamic algorithms for this KH coloring problem. And one key operation, or two key operations actually, are swap out and swap in. So if I have an edge E that is assigned some color, like the red color here in this example, by swap out E, I mean that I'm looking at the edges incident to the edge E on both end nodes, and I'm trying to find two edges that I can color with this red color and that have together larger weight than E had. This would be a successful swap out operation.
Can I ask
Yes.
a context, just to get the context for from the application? How large are these graphs? And if you're supporting this big computation, how much time is spent doing the updates to this graph compared to the actual computation, the actual problem that these computers are trying to solve?
So we did experiments on real-world traces, or data from data centers, and there we had the communication demand graphs had thousands of nodes, but not much larger. We also ran experiments on large instances, but they were generated because we couldn't get such instances. We couldn't get such instances, we couldn't get such real-world instances, so we generated larger ones and also evaluated algorithms on this. But yeah, the real-world instances had like a couple of thousands of vertices, and some of them were pretty dense. So. Does this answer a question? Oh, I think it was a second question.
The other question was, if this is being done in the application in support of some larger computation,
yes,
how much time is spent even in the slowest version of even in a static, if you didn't use dynamic algorithms, what percentage of the time is spent doing this as opposed to the actual computation you're trying to support? I'm trying to see, does the speed of this dynamic algorithm matter in the broader context?
Yeah, that would be interesting to evaluate. So far, we haven't tried it. So we only concentrated on computing the configurations, and we assumed that this is done on some dedicated hardware, and we can do it within microseconds or a few milliseconds, like update these configurations. But so far, we haven't evaluated what it actually means for the speed up of applications that are running, or how it can improve the throughput in the network, actually. So this would be future work for us. We are looking into it. Right. So yeah, coming back to those two primitive operations, swap out. I already explained, and swap in is sort of the opposite. So for swap in, I'm giving an edge E that is currently uncolored. I'm looking at a specific color, like the red one here, and I'm trying to color E with this color, with the red color here, and uncoloring the two adjacent edges, but only if this leads to an increase in the total weight of the colored edges. So only if E has larger weight than its two adjacent edges. And based on this, we designed a randomized dynamic greedy algorithm that takes two parameters, alpha and beta, which I will come to in a minute. So what it does is, in fact, whenever we have a weight update on an edge E, so the weight changes by some delta. If delta is positive, so the weight of the edge increases, and the edge E is currently uncolored. If it's colored already, we don't have, there's nothing to do for us. So, but if it's currently uncolored, we are interested in coloring it now. So we first check whether there is a free color C prime on both end vertices. And if this is the case, we just color the edge with this color and we're done. Otherwise, we're looking at up to beta colors that are drawn randomly from our set of K colors. And we are looking at these at the swap-in operation for all these colors and trying to find the best one here. If this swap-in operation is successful, this means that there are two adjacent edges that are now uncolored. So we just try to color those edges again. So we recurse here, but here the first parameter comes into play. We only do this for alpha minus 1 times. So alpha limits number of recursive calls here. The second scenario where we have to take action is that the weight of the edge E decreases, so delta is negative, and the edge is colored. Then we again look at up to beta incident edges on each end vertex, and now we look at the swap out operation. So we try to uncolor E and see whether we can find two adjacent edges that together have larger weight and can be colored with the color that E had previously. So if this is successful, then this means that E is now uncolored. So we try once to color it again, but we don't do any recursive steps here. So this is our dynamic greedy algorithm, the first one. We also designed another dynamic algorithm that is based on a static algorithm called KEC. KEC just means K-edge coloring. So this KEC algorithm was interesting for us because it turned out to be the best, or the best static algorithm for this problem in an earlier study. So KEC, just to give you some context, is an adaptation of the delta plus 1 edge coloring algorithm by Misra and Gries, if you are familiar with this algorithm. It is modified because we have a special situation here with edge weights and a limited number of colors and so on. So for reasons of time, I cannot go too much into detail here, but this is another dynamic algorithm we designed. And then we also designed post-processing routine that maintains the following invariant, that for each uncolored edge E and each color, C, this color C is not free on both nodes, and swap in for this edge, and this color yields no improvement. So in fact, this means that for each uncolored edge, there is no, I cannot perform a swap-in operation for any color, basically. And if we maintain this invariant, then we know that our solution is a 1/2 approximation. So, well, this is an invariant that can rather easily be established. We can either apply it as a post-processing, and if we do so, I will append a suffix of -p to the algorithm name, or we can just call it standalone, and then we call this algorithm batch 2 approx. Then we looked at the filtering approach, where the idea was that if the weight of an edge only changes a little, then this probably doesn't have a large effect on our solution. So if we filter out those updates, ignore those updates that only change edge weights by a little amount, then this should lead to a speed up of our algorithm and maybe also improve the recourse. So we did this here. In fact, we compared the new edge weight to the old edge weight. And if it was in the range of 1/t and t, where t is a parameter, then we ignored this edge weight change. And this can be applied as a pre-processing to any algorithm, in fact, so just filter out the updates where the weight doesn't change sufficiently in this. And algorithms, if you use this for an algorithm, then we use the suffix -f to show that this is applied. We also then designed some hybrid algorithms. So the idea was that in some cases, if you have like only a few changes to the graph, a dynamic algorithm may be faster because it only needs to consider the updates themselves. But if we have a lot of updates, if, for example, the entire graph changes by a batch of updates, then a static algorithm may be faster. So for our hybrid algorithms, we try to find a balance between these two. And the hybrid algorithms use a dynamic algorithm if the size of the previous batch was smaller than the number of nodes in the graph, and otherwise it uses a static algorithm. So this is, of course, a heuristic when to switch to the dynamic algorithm when you use a static algorithm, but we found that this was sort of a good rule. So we have two dynamic algorithms, the DIN-greedy and the DIN-KEC that I already mentioned. And for the static algorithm, we only used the KEC, which, as I mentioned before, showed the best time for quality trade-off in prior work. So combining these gave us a hybrid greedy and a hybrid KEC algorithm. We also designed several batch dynamic algorithms, which I did not include here for reasons of time. Also because in the empirical evaluation, which I will talk about next, they did not play such a huge role. So for our empirical evaluation, as I mentioned before, we did those on real-world instances. So we had 30 instances that were obtained from Facebook data center traces, a collection called pFabric, and then also some traces from high-performance computing. So in fact, we had communication data here, like packets with a source and destination, a packet size, and a timestamp. So the timestamp of each packet told us the batch. So all packets that were had the same timestamp correspond to updates that we grouped within a batch. And the packet sizes told us the edge weight. So we had various batch sizes. They could be rather large, up to 66.4 K. And also we had instances where we had up to 5,000 batches. What did we find? What you can see here are results for K equal to 8. So we have 8 optical switches here. We did experiments for K between 2 and 64, I think, 32 or 64. So the results shown here are for K equal to 2. You can see the box plots, which tell us the time per update for each batch. And the diamond gives the geometric mean of the update times. And on the right side, you can see the geometric mean weight, which is shown as a star in the plot. So for the stars, we want them to be as far to the top as possible. And for the boxes and the diamonds, we want them to be as low as possible. So on the very left, this is the static algorithm KEC, which we used for comparison and as a baseline, sort of. So you can see that it has it produces very good solutions. The star is this is the furthest to the top, but the running time can be rather large. Then next are the two hybrid algorithms. And you can see that they have a sort of similar quality as the static ones, but they are faster, and often even much faster than the static one. Then among the batch dynamic algorithms, only the batch 2 APX is included here, which guarantees this 2 approximation, this 1/2 approximation. This was actually the only batch dynamic algorithm that was competitive. It was especially good on the p-fabric instances. The dynamic algorithms, which are shown next on the plot here, their 2 versions were best, or in fact, among the dynamic greedy one, the one that used the post-processing, the filtering, and picked just, so if this beta parameter was set to 1, so we just picked one color randomly for our swap-in operation. This one showed the best performance, the dynamic KEC version, also with post-processing and filtering, similar but slightly slower. So these are these 2 here. Post-processing generally was efficient and efficient. It cost some time, but it was effective for all algorithms except for the KEC and the hybrid KEC. So apparently these algorithms did not need the extra post-processing. Filtering turned out to be effective in reducing the running time, but also reduced the solution quality. So it turned out to be only useful if combined with post-processing. Then we could get the improved solution quality from the post-processing and the reduced running time from the filtering. And when looking at the recourse, was as sort of expected, the dynamic algorithms had this lowest recourse. Hybrid were a bit worse, and the static algorithm had the largest recourse.
How important was recourse for the application?
Well, it means basically, yeah, it measures how many reconfigurations I have to make to this optical switch. I was told that it is not the most important criterion, so speed would be, running time would be more important here. And solution quality, of course. Then we found that, unfortunately, sort of, our real-world traces only had a temporal resolution of 1 second, whereas our optical switches can be reconfigured within microseconds. And you can see, I don't know if you can read this, but also the update time is, yeah, a microsecond or less. So we also wanted to simulate higher reconfiguration frequencies, and we just split up the batches into sub-batches with limited edge weights and generated another 26 instances from that. And just want to go over this quickly. So this picture, the overall picture was similar. There are some differences. Filtering, for example, had no effect here due to weight limits. The hybrid algorithms were similar to the static algorithm in all respects. The fastest algorithm here in the set were the dynamic greedy without filtering, and the batch 2 APX algorithm, especially if K was small. For recourse, we have a similar results as before. And post-processing, again, was very effective, but had an effect on recourse. And as I said before, we also did some experiments on synthetic instances because those real-world instances were rather small in comparison. So we generated graphs using an armored generator. Edge weights were drawn from exponential distribution. This allowed us to create larger instances and also control the fraction phi of updated edges per batch. So you can see the plot for k equal to 2, 8, and 32. The speed up of different algorithms over the static KEC algorithm. So this is would be the one line here shows the running time of the KEC algorithm, and the further up, the larger the speed up over this algorithm. What we found is that the dynamic and batch dynamic algorithms are faster than the static algorithm if phi was small, if it was at most 0.1. The speed up decreases as k increase. Okay, so if you go to larger k, then the speed up decreases. You can see this here, and also as phi increases, the speed up of the algorithm decreases in comparison to KSC. Generally, the hybrid algorithms were faster than the static ones for small phi and equally fast for larger, so this is good. It means that hybrid is somewhat superior to KSC with respect to running time here. The solution quality was closer to the static one for larger k, but for small k, it could be even less than 90%. So for small k, the hybrid may be not the ideal choice. Interesting here was also that the batch 2 APX algorithm always produced solution quality within 3% of the static KEC algorithm, which is very good. So in summary, which algorithms should one choose? Those are the interesting candidates in some way. So if we have small batch size and k is small, our recommendation would be to go for this batch 2 APX algorithm. If k is a bit larger, then one should go for one of the 2 dynamic algorithms. If we have large batches, then the 2 hybrid algorithms are good choices in our opinion. If you don't know anything about your instance, we also recommend to go for hybrid algorithms. If you say that quality is the most important issue, you do not care so much about running time or recourse, go for the static algorithm and you'll get the best solution quality. And if recourse is the most important thing to you, don't care so much about solution quality, for example, or running time, go for the dynamic ones. And yeah, this source code is also available publicly on GitHub. So if you're interested, you can try this yourself. Okay. Any questions?
You probably have to repeat it.
So I've heard the word adversary a whole bunch. And is there an opposite of an adversary? Like if you had an Oracle scheduler that knew every past and future change that was going to make, like how much better could it do in terms of quality? Like twice as good, 8 times as it, like?
Oh, that's a difficult question.
Or runtime. I'm just wondering how far you are away from the perfect.
From perfect with respect to running time? No.
Runtime or quality or whatever metric you happen to pick. Like, you know, are you 1% away or are you 5 times as bad or like what would, you know?
Okay, so it really it depends a lot on K. So the larger K, the better your algorithms become. For the static, well, we looked at this problem in the static setting. We also actually computed the optimal solution, and we found that, for example, this KEC, which we use as a baseline here, comes really close to the optimal solution, but significantly faster, of course. I don't remember how much close to BIM, how close actually. I mean, we have a 2 approximation guarantee here, so we are at least within 50%. But experimentally, I think we were much closer, like I think over 90%.
Okay.
I would have to look that up.
I just, order of magnitude was helpful. Like, you're much closer than your approximation.
Yeah.
That's cool.
Yeah.
Okay.
Okay. Yeah, the other problem I wanted to talk about is a very basic one, reachability. So I think you all know what's meant by reachability. In fact, we can look at 2 settings here: single source reachability, where we keep the source vertex fixed. We only are interested in whether some vertex T can be reached from the source vertex S. So our query consists only of 1 vertex T, or for all pairs reachability, also called transitive closure. We give both vertices actually S and T, and we ask whether there's a directed path from S to T. So when we started to work on this problem, there were 2 experimental studies so far. They were very large. one by Frigioni et al. And the other by Komidas and Sariliagis. And they compared many fully dynamic algorithms, also pseudo-fully dynamic algorithms, to static graph traversal. And what they found was that the fastest algorithms in most instances were those static graph traversal algorithms, like BFS, DFS. And the strongest competitors of those algorithms were actually fully dynamic extensions of two partially dynamic algorithms that maintain strongly connected components. These two were, one was due to Italiano originally, and the other Roditi and Zwick. And they were made fully dynamic by the authors of the study. But they could only beat the static graph traversal algorithms if either the graphs were very dense, or there were very few queries. And also in this studies, the instances were mostly random and very few were random, were real world. So when we started to look into reachability, we first looked at the single source reachability. And then at some point we already had single source reachability algorithms which performed very well. And we were thinking of using them to solve the all-path reachability problem as well. So I'm going to talk about all-path reachability here. And our idea was the following. Suppose that we have a vertex V, and for this vertex, we know the set of vertices that V can reach. I will call the set R+, so like sort of out reachability, and the set of vertices that can reach V, so sort of in a set of inreachability. So for V, I know these two sets of vertices. Now, if I have a query whether vertex S can reach a vertex T, what I could try to, or how I could try to answer this query is, if I know that S can reach V because S is in this in-reachability set of V, and T is in this out-reachability set of V, then of course I can immediately say that S can reach T, just using this information for V. Also, if, for example, S can be reached from V, but T cannot, I can immediately say that then S can also not reach T. And symmetrically, if I know that T can reach V, but S cannot, then I also know that S cannot reach T. So from these three observations, the first one gives us a positive answer, reachability, S can reach T, and the other two give us a negative answer. And we call it V supportive vertex. So for because it supports us in answering reachability queries. And then we built a couple of algorithms around this idea. So in general, the idea is that we store a list of supportive vertices. And for each supportive vertex, we maintain the set of out and in reachable vertices using single source and single sink reachability algorithms, dynamic algorithms here. Whenever an update comes, an edge insertion, deletion, we just forward these updates to these SSR algorithms. And whenever a query comes, we just try our supportive vertices in some order and see whether we can answer the query via one of those observations. And if this is not possible, we fall back to static graph traversal. So what's not specified yet is first, how do we pick our supportive vertices? Then do we something in addition to just forwarding updates to those SSR algorithms? And how do we, well, pick the order in which we query the vertices to support us for answering reachability queries? So in the end, we came up with three algorithms, SV, SVA, and SVC. SV and SVA, so SV is the simplest one. It just picks k vertices as supportive vertices during initialization. So it first sees the graph. And then it sticks with those. SVA does the same for initialization. So pick k vertices as supportive vertices, and they are picked uniformly at random from the set of 4 vertices. SVC uses strongly connected components to pick good supportive vertices. So it first computes the strongly connected components of the graph, and then we have some threshold parameter set. If a strongly connected component exceeds the threshold, then we pick a supportive vertex for this component as representative, and we maintain a map that tells us for each vertex the corresponding representative if it exists. But an update comes, in addition to forwarding the updates to the SSR algorithms. For SVA and SVC, we reinitialize our data structures every C updates. So C is another parameter here. And this is also the only difference between SV and SVA. So SV does never reinitialize. It sticks with its supportive vertices that are picked at the beginning. When a query comes, then SV and SVA just try the supportive vertices in the order they were picked, so no specific order. And if they could not answer the query using those vertices, they fall back to static graph traversal. SVC can look up and use the representatives. It may find that the representatives are no longer valid because there have been changes to the graph and we haven't recomputed our strongly connected components. In this case, invalid entries are just removed from the map, and then it falls back to the mode of SV and SVA. So it does not try to fix the strongly components in any way. This only would happen every C updates during this reinitialization. And then we ran some experiments for these algorithms. So if we look at the update times, then you can see the purple algorithms are the SV algorithms using 1, 2, and 3 supportive vertices. And you can see quite well that each additional supportive vertex increases the update time. The 2 green lines correspond to the SVC algorithm that maintains the strongly connected components. And you can see that, for example, in fact, they both use only one, maintain only one strongly connected component most of the time, so for medium to large densities. And this reinitialization, which happens here and also for the blue ones, the SVA algorithms, this is quite costly, so it increases the update time quite a lot. If we look at the query time, here we have also the static algorithms included. So those are the typical traditional DFS, BFS algorithms. They appear. Then we implement a bidirectional BFS, which was way faster, but still a lot slower than our dynamic algorithms. So you can see here that the fastest algorithms to answer the queries were the SVC algorithms. Then this SV algorithms using 2 or 3 supportive vertices, and here's the one that uses 1 supportive vertex. The line comes down here, and then also uses almost no time to answer queries for the denser graphs. So if we put everything together and we say we have equally many insertions, deletions, and queries, then this is the result. So unless the graphs are very sparse, where the bidirectional BFS is competitive, the dynamic algorithms are much faster. The fastest ones are, in fact, for the sparser graphs, the SVC algorithm that never reinitializes here, and the SVA algorithm that picks just 1 supportive vertex. And this picture also does not change if we go to larger graphs with 10 million vertices. In the interest of time, I will skip over this. We also did experiments on stochastic Kronecker instances, equally many insertions, deletions, and queries. The fastest were, again, SV1, SV2, and the SVC algorithm, which reinitializes the fewest. The static algorithms were far from competitive. And we have the same picture if we look at real-world instances. These are hyperlinked networks. Again, twice as many updates as queries. Again, the fastest were here, SV1 and SV2, and the static algorithms were not competitive in any way. So which algorithm is the best? We think those three are the interesting algorithms, where SV2 in comparison to SV1 has a more stable query time, but double update time. And SVC also has a more stable query time. It is fast on sparse instances. So if you have sparse instances, it's maybe the better choice. But yeah, update time is considerably increased. It would be interesting to see what happens if we reinitialize even less often. So this is something we are currently working on. And yeah, slower by several orders of magnitude, the static algorithms. Which I think is nice because it shows that dynamic algorithms actually work in practice. Right. Okay, I will also skip this because I only have 2 minutes left. So I wanted to talk a bit about engineered dynamic graph algorithms in the remaining time. So generally, what does it mean to experimentally evaluate dynamic algorithms? The first question is, what do we want, or what do we need to measure? Usually, we want to measure solution quality. Running time is usually very important, sometimes also recourse, memory, communication, I/O, whatever. So I want to focus a bit on running time here, because for dynamic algorithms, the next question immediately is, what exactly do I want to measure when I talk about running time? Am I interested in initialization time? Usually not so much, because if I have long update sequences, the initialization time is not so important. I'm more interested in how far can I process the updates. Okay, I may be interested in the update time, or the time to process an entire batch of updates, or the query time. But then the question is, am I interested in the time for each update, each batch of updates, each query? Or am I just fine with getting a total time, like the total time for the entire update sequence, for example, maybe even intermixed with queries? And if I'm interested in single update or query times, well, this often gives interesting insights. You can, for example, see whether insertions or deletions are faster, or also how much this fluctuates. But this is also a challenge in many cases, because the time for a single update or query can be very, very small. So the experiments here become highly sensitive to all kinds of interferences from the system our experiments are running on. So what one can do about this is first repeat experiments multiple times. I mean, this is a gold standard anyway in algorithm engineering, but it's even more important if you are trying to measure such small running times. And second, prepare the system for benchmarks, prepare it well. So reduce other processes, try to run, stop all other processes that are not needed, have a dedicated machine where to run the experiments on. Disable frequency scaling. You don't want your CPU to go to power save mode in between, or something like that. Also be aware of NUMA architecture. So how expensive is it to access some memory? This may not be the same cost in each case. And one more thing, when measuring such small times, you may consider whether to include or exclude the update time that your underlying graph data structure actually needs to, for example, insert an edge into the graph or remove an edge from the graph. Because if you have very, very small update times, you may, in the end, just measure the update time of the graph data structure rather than the update time of your algorithm. So it depends on how complicated your algorithms is, or how efficient the graph data structure is. But usually you want to say something about the algorithm and not necessarily about the graph data structure. Right, what about dynamic graph instances? So currently there are a couple of dynamic instances out there, but they are hard to get. So sometimes one gets edges with timestamps, but then they are insertions only, and there are some specialized graph generators also. But what people do usually is doing some undoing approach, sliding window, remove and add, or morphing, a snapshot approach. I think we've heard this before, so I will not go into detail here. What I haven't heard so far is or I think it's an open problem. If the algorithm does not maintain a solution, it may be relevant what queries I actually use to evaluate my algorithms. Do I use random queries, or are there some sort of real-world queries? I don't know. And this is the last slide. So what else can influence experiments? Memory usage and cache effects. We've heard this. Characteristics of the update sequence. Do insertions, deletions appear in groups or intermixed? Do the updates build up or dismantle structures like paths? This can have a huge influence in my experience. Edge lifetimes. How long until an inserted edge is removed again? So here you can see different examples of a random graph, one random dynamic graph, one that was created from different snapshots, and the last one is a real-world dynamic graph. And they look quite different, I think. That's it. Sorry for going a bit over time.
So we have time for, let's say, one quick question.
Hi, great presentation. I just have a quick question about the data sets you used for your reachability experiments. So for your random graphs, how did you generate the random graphs of different densities?
For the random graphs, these were ER graphs, Erdo-Shreni graphs.
Oh, Erdo-Shreni.
Yeah.
But for Erdo-Shreni graphs, if I'm not incorrect about this, they have good expansion properties,
Yes.
expander properties,
Yeah,
right?
yeah.
So the other question is is it interesting to test your algorithm, all these algorithms on high diameter graphs? Are any of the real world graphs that you tested on, do they have high diameter?
I haven't looked into it.
Mhm.
I'm not sure. Yeah, I would have to look it up.
Okay, thank you.
All right, then let's thank Kathrin, and we ask question offline. Thanks.